Good afternoon, professors, students, and colleagues. Welcome to join Innovating to TechTalk today. Today, we are happy to have Dr. Bruno Oliveira, Associate Professor from Department of Computer Science, to be our moderator. Without further ado, Dr. Oliveira, please.
Hello, welcome everyone to this Tech Talk. The Tech Talk is a series of forums and dialogues given by engineering researchers of diverse academic backgrounds to share their insights on innovation-related topics. Today we are going to have Sérgio Lourenço with us, and he's going to talk about soils by design, a reality, not a pipe dream. So let me say a few words about Professor Sérgio Lourenço. So Sérgio Lourenço is an associate professor at the Department of Civil Engineering at HKU. He joined in 2014 from the School of Earth and Ocean Sciences at Cardiff University in the UK. And before that, he worked on Geotechnical Observations Limited in London. Sérgio has degrees from New University of Lisbon, Kyoto University, and Durham University, respectively, for his undergraduate, master, and PhD studies. So Sérgio is currently developing functional granular materials for climate adaptable infrastructure, and he has had several sources of funding in the past, including the UK Engineering and Physical Sciences Research Council and the Royal Society. And Sérgio is also the current recipient of the 2022 British Geotechnical Association Medal, jointly with Yao Ting and Beatrice Baudet. Okay, without further ado, let's have Sérgio get started.
Okay, so yeah, thanks very much, Dr. Oliveira, for the introduction. And yeah, my name is Sérgio Lourenço, and I work very much. I simply work with soils, and I've been working with soils for a long time. So what you have here is, just for your information, these are sand grains being observed in a scanning electron microscope, and what you see right on the surface is some water drops. So that's condensation of water on sand grains. So it's all quite pretty. And I'm showing there sand grains and water because throughout the talk I'll be talking about water, its effects on soils, and how can we minimize such effects on soils. So yeah, so I'll assume that perhaps some of you don't think much about soils, so I'll be providing a more general introduction and background information about it. I'll be talking about soils mostly from an engineering perspective, using it in construction, using it as a construction material in engineering or civil engineering projects. This means that we have to move on. There are new things coming up. So we talk so much about climate resilience and delivering net zero, so I'll be mentioning that. How do we design structures nowadays? We are currently moving away from that. And then towards the end, I'll be mentioning about some of our work and, let's say, some more advanced work on how to change soil properties to fit very specific applications. Yeah, so I've been working with soils, and all my background and all my life, academic life, the last 20 years has been on soils, starting at first with rainfall-induced landslides, and then moving. Actually, with time, I have been moving smaller and smaller and trying to look at very small scales, because when you deal with soils at such small scales, and you change the properties, you change the particle characteristics at such small scales, it produces effects at a larger scale, which are quite obvious. So yeah, so maybe I'll really go back. And so soils are very much granular materials. They are discrete materials. They are particulate materials, which means that they can have different particle sizes. They can also have up there some water. Again, in between the grains, what you have there is some water condensation. And on the right-hand side, down here, you have clay. So these are clay aggregates. So if you look at the scales, all these pictures show very different sizes. So whenever we deal with soils, we look not only at the particle size, we will look at the particle shape. In this photo, this is sand. You can see different colors. The different colors can correspond to different mineralogies, materials with a different origin. So all of that is going to affect how soils behave as engineering materials. And soils, yeah, well, soils certainly support several sectors of the economy. You have up here something that is quite of interest to us, transportation. So you have here a highway embankment. So this embankment uses soil. If you move a bit further down, you have down here energy. So energy, an example, something quite recent. It makes use of the properties of soils. So soils are very much at a constant temperature. So this temperature changes between the seasons, winter and summer. So this temperature can then be used as a source or as a deposit of temperature, of heat. And it can be used to cool or heat structures out there. They can also be used as construction materials. And you have an example here. These are the Tolu buildings in Fujian province. So if you simply mix sand and clay, and you mix as well with some water, you allow it to dry, it will turn into a solid. And you can actually use it as a construction material, and it will last for a very long time. So that's the historical heritage that you have there. Obviously, soils are critical for food security, agriculture, but that's already beyond the scope of this presentation, and I'll not be mentioning about that. So something, so whenever we talk about soils they are certainly very sensitive to the presence not only of water, but whenever you change the amount of water in soils, you are going to have issues. There will be some weather-related hazards. So Hong Kong is quite famous for some of them. You have here landslides. This is a very famous one that just happened outside the campus that way. Poshan Road landslide in the 70s. So that happened because soil saturated quite a lot with water. There was water pressures there that triggered that failure. But if you allow fine soils to dry, they shrink, which means that they reduce their volume. So if you have buildings, if you have structures on top, they are going to crack. So having too much water or having too little water in soils is an issue, especially when you change. So this means that everything we have been talking so far about climate change is extremely relevant to soils, because if the weather patterns are going to change in the future, I don't know, extreme rainfall, droughts are going to become more frequent. So some of these events will also become more frequent. And this is taken from the latest assessment report, IPCC, which came out just 2 weeks ago, and they mention damages to infrastructure as very likely because of an increase in the temperature of 1.5 degrees Celsius or more than that. But soils soils are granular materials, and this means that you have a series of particles, and these particles can move. So soils deform as well, and they can deform over time. And you have some very famous examples out there. You have Pisa Tower. Well, it's leaning not because of the structure itself, it's because the soils are quite soft. These are clays, and they deform over time. Other examples as well, Big Ben is actually leaning just 0.26 degrees to one side. It's on top of London clay. It's, again, clay deposits. So what this means is that over time, soils will change. And perhaps some of these weather-related effects can accelerate these things or not. I'm not going, so I should be careful, I'm just saying. But we should also try to see whether there is any relationship there. Obviously, creep is not really such a big thing in Hong Kong, but soils in Hong Kong have this, internal erosion. So here, soils are quite sandy. So this means that you have fine particles, large particles, and the fine particles can wash away with water. So soils over time can become more porous. So what this means is that we need to deliver climate-resilient structures, we need to find technologies to minimize wetting and drying of soils. And we should treat soils as materials, and which means that we also have to find technologies to repair soils. As you would have heard, we talk so much about, nowadays we have to be working towards a carbon-neutral economy. I'm establishing a parallel between three regions, let's say. So you have EU has a target, which is 2050, and a reduction in the greenhouse gas emissions of by 55%, by 2030. They do have some action areas. This is all related to energy, but it's also related to materials. When we compare it to Hong Kong, and this, I think it came out recently, Hong Kong is rather similar, 250 climate neutral, so same thing. Perhaps a little bit less ambitious, 50% reduction by 2035. But when you compare it to Copenhagen, for example, they want to be carbon neutral by 2025. So that's in 3 years' time. So they are quite ahead. So this means, in practice, that we have different time scales to reach this climate neutrality. So in Hong Kong, we have a little bit more time to work on trying to reduce the greenhouse gas emissions. If you go back to the same report, the sixth assessment report that came out 2 weeks ago, they do talk here about construction material substitution. So it's important we go beyond things like concrete, using raw materials, so that we can reach this climate neutrality. So the way we build and even the way we use soils has to change. So these things are actually becoming quite frequent and quite, they're coming in vogue. You have carbon labeling now coming up. It says in there, in green in here, it says what is the carbon dioxide equivalent production for that particular product. So these things are now coming up in our daily lives. So then how do we design structures? How are soils used? I showed you before this image. This is the highway embankment. So in this case, you have a soil there. That soil would have been transported. So perhaps you have to excavate it from somewhere, bring it there. So there will be a greenhouse gas emission for that. Down here, you have a very famous example. Just here in the campus behind Hacking Wong, you have this massive retaining wall. And that retaining wall has all these white bits. So these are anchors. So these anchors are steel cables that lock the rock mass against the surface. They are pulled, so they are under tension, and they simply compress the whole rock mass and make it stable. So here there is plenty of concrete, there is steel. Obviously, these solutions can still happen in the future, but maybe we have to start working on finding alternatives if we can avoid it. So alternatives are actually coming up. And one of them is that we are moving towards a substitution of soils, for instance. So you can use waste byproducts. So soils are granular, So anything, very much anything that is granular out there, we could try to replace it. And an example, construction and demolition waste. This is fine, this is perfectly acceptable. All this material could be used, for instance, down there. Mine tailings, not relevant to Hong Kong, but many other areas. Energy production, you have there fly ash. So fly ash is just this. You can see it's granular. There is quite a lot of work done on universities in trying to use that as a replacement for sand, as a replacement for soil. You have other things coming up. This is not really a waste, but biochar is actually carbon negative, so we can certainly have it in soils. And it should be fine in a soil. It shouldn't create any issues. You may have heard about green infrastructure. I have a colleague working on porous pavements. So this is mostly to drain water to prevent flooding. And you also have nature-based solutions. So in this case, a very simple example is that you can use live stakes. So these are pieces of wood which are inserted in the soil. And it needs to be the right species. It will grow over time, and then you have there quite a lot of vegetation. So this means that, for instance, the benefit here is that, I mean, it's a nature-based solution, but then you will prevent, for instance, erosion on these soils, on these materials. So we have to, the way we deal with soils and we use soils is okay, is fine, but we have to change it, mostly because of, we have to bear in mind that there are the weather patterns are changing, so we have to find here some, perhaps you could start working on technologies to minimize wetting and drying effects, technologies to repair soils. We also have to deliver to net zero, so this means using less raw materials, more green solutions or green materials. However, there is a challenge here, and one of them is anything we put in the soil, we have to make sure that it's, we have to check its environmental impact. So not only should it not contaminate the soil, but it should not interfere with vegetation. It should not interfere with humans as well, because soils are at the interface with the atmosphere, with vegetation, and us. I think we can handle that. There could be solutions for that. Maybe this is something which may be a little bit more difficult. That is, the way structures are designed is that they are designed for a very long period of time, 50 years, 100 years. So anything we put in a soil has to last and has to keep its properties for that amount of time. And this could be an issue to deliver. So perhaps we could change our approaches and how we deal with soils and how we use them. Perhaps we could use or change soil properties only when needed. So we don't need to change soil properties permanently, but only when the soil is asking for it. So this is then the soils by design approach that you see up there. So we can actually try to tune soil properties at a very small scale, very carefully, so that they fit into specific applications. So this will involve here a cycle. So first we create these technologies, we characterize them, we check whether they work. We can use computer simulations to analyze all this data, to propose alterations and make new technologies and go again around. So what I'm going then to show now is a couple of examples of let's say some of this more advanced work that is happening on soils. And I'm going to start with, well, I guess we can call this bioengineering. So this is an area which is becoming quite established. I don't think it's established in practice. I guess to reach practice, it will still take quite a lot of time. But within bioengineering, I split it into two parts. The first one is vegetation. So using vegetation in soils has many benefits. It can also have some disadvantages. But one of them is that trees have roots, as you see there. And these roots hold the soil together. So if you have a slope, for instance, with vegetation, you can reduce or you can improve the slope stability. You can make slopes more stable just for having them there. This means that you can select which trees are more compatible, which root architectures are more compatible with a particular soil for a certain application. And what I'm showing here is actually a project, ongoing project. This is being led by Dr. Anthony Leung at HKUST, and he's looking at the behavior of trees during storms, during typhoons. So Hong Kong has typhoons, and in Mangkhut, 2018, many of these trees came down. So what he's currently doing is literally pulling trees out. This is all fine. It's all, he can do it. He's measuring the force that it takes to pull these trees, and he's relating then, the aim is to relate this force to, for instance, the wind speed when you have your wind coming from a typhoon, so that in the future we can come up with species which are more resistant to typhoons. Another area where there is really quite a lot of work right now is biocementation. So biocementation is quite simply, well, soils have certain properties, but usually the properties of a particular soil, mechanical properties, they may not be good enough for us. So we improve them. And you can improve it by cementing the soil. If you just add cement, that's fine. But you can also use bacteria to do the job. So in this case, you can have your soil with bacteria. You have to add some food to the soil. And in the right conditions, your bacteria is going to precipitate a cement. In this case, it's carbonate calcium. Carbonate calcium is very common. And some rocks are made of carbonate calcium. Calcium is not common in Hong Kong, but many other places in the world it is. So what you have here is a sand grain, another sand grain, and some carbonate calcium right in the middle. So this is all very, let's say, very natural. But you do need to have the right conditions in terms of temperature, pH, for these things to happen. So this is establishing in itself as a field, and we call this, it's now starting to get called, and there is a new journal coming up called Biogeotechnics. So these two are quite established. In our particular case, we are trying to look at soils and trying to change their properties at an even smaller scale. So a big advantage of soils is that they have a very large surface area. So if you think of a soil, it's grains. And you can have a certain volume or a certain mass of soil with many grains. These grains have surfaces. And it's the surfaces of the grains that are in contact with each other. So the properties or the way the soil behaves will depend on the interaction of the particles. So it's surface against surface. So if you change the surface of the particles, you will be changing the way the soil behaves. And this also includes the interaction of the particles with water. So what we started doing already some time ago is try to make soils hydrophobic so that they could be used as a barrier for water to infiltrate. We can control how hydrophobic the soil is. You have here a lotus leaf, so this is super hydrophobic. This is actually a soil with a water drop on the surface. This soil is natural. But if we use, for instance, those compounds that you see there, you can actually make whatever the soil hydrophobic. So you have here sands. So these are the typical geotechnical materials. You have sand, you have silt, you have clay. These are water drops. Here there is a sort of a nautical effect, but the drops are sitting here and they don't go into the soil. This is achieved because we are simply coating the surface of the particles with films. And these films are extremely thin. They have some few nanometers to 1 or 2 microns. So if you touch the soil, if you look at the soil, it looks the same as untreated. But the effect it produces at a larger scale is quite, is obvious. We have also, obviously, we have spent some time around this. We have tried to recreate that surface on soils. So these are sand grains with a powder. because if you touch a lotus leaf, it actually feels quite rough, velvet-like. So this means that the surface of a lotus leaf is very rough. So we were trying to recreate that in sand grains. Okay, it improves a little bit, makes it slightly more hydrophobic. So where do we use this? We use it as an interface, as a liner, as a cover material. And the plan here is to use it for instance, slopes, but anything where, or any situation where you have a soil in the field, you go, you treat it, and you use it. So you have flood defenses. You could use it to isolate another problematic soil, expansive clays. They swell and shrink, so they are not good. Waste containment. If you have groundwater, which has a chemistry which can be quite aggressive towards buildings, you could use it as an interface with the structure. You have the tracks as well. So this is in general. It has also been proposed to use it in more specific applications. So in cold regions, you have freezing and thawing, or in areas where you may have freezing and thawing. This means that for the case of pavements, your freezing and thawing is going to generate volumetric changes, and that will crack the pavement, which means it will need to be improved and replaced. So if you make the soil hydrophobic, or so you create some hydrophobicity there will not be wetting, and you will be preventing that. The same thing for arid regions. In this case, soils can be quite rich in salt. Salt is corrosive in contact with structures. So again, you could perhaps use some of these hydrophobic solutions to avoid water to reach your structure. So this is all under technologies to minimize wetting. We have spent some time working on it, so trying to test a variety of compounds, how these materials behave, using it on slopes, looking at their durability, and trying to recover this hydrophobicity. Just to give you some idea of the sort of work we do, so in this case, we create a new material, and it's usually not enough just to create it and say, oh, it's hydrophobic. So we have to check whether other properties are affected. So what you see here is a mechanical study. If you look there, this is 2 grains of sand, and they are vertically touching each other, and then we apply a vertical force, kind of downwards, and then a horizontal force. So what you have here is that, so you push the 2 of them together vertically, and then horizontally to shear. So what we found is that these coatings, whatever we use, they tend to be quite soft, or they are softer than the mineral itself. So this means that if you push vertically just a little bit, the shear behavior is going to be controlled by the coating itself. But if you push vertically quite a lot, it will break the coating, and the shearing behavior will be controlled by the minerals, by what the grains are made of. We also looked at durability. So durability here means, as any material, we simply subjected it to accelerated weathering. What is this? We create these samples, and then we subject it to cycles of wetting and drying, heating and cooling, freezing and thawing. So it's all very extreme, and we see how the material behaves. Obviously, this is the beginning. You can actually see shrinkage going on. So the coatings are responding to it. Here, this is an abrasion study. So we simply put it in a drum, and we rotate these materials with steel balls to force the breakage of the particles and the coatings. And yes, on these very extreme situations, the coating starts detaching, exposing the underlying material. We also did a study on slopes already some time ago. Well, this is a rather simple arrangement, but what you have here is, this is a flume. You have soil there. This is, on the sides here, it's all made of glass, so you can take photos of it. You can also instrument the soil here with instruments to measure water content, and there is rainfall up there. And this is a profile of water infiltrating throughout the soil. This wetting front rate is how fast does water infiltrate. And here you have 3 samples. This is untreated, slightly water repellent, and very water repellent. So when it's very, certainly no water gets in. If you make it a little bit, some water will get in. If you don't treat it, water moves all the way down. Okay, so these are then the technologies to minimize wetting. And now I wanted to move into the technologies to repair soils. So soils, for sure, they will degrade over time. Something will happen and we'll need to fix them eventually. In other fields, and an example is in cementitious materials, concrete, they have been doing quite a lot of work on using microcapsules. So in this case, you have concrete, you mix it with these capsules. The capsules are going to have a cargo. This cargo is released, and it releases a substance which is at the beginning liquid, but eventually it will solidify and it will fill these cracks. So this is a self-healing approach. You may have heard about self-healing concrete. This is being done not only on concrete, but also on asphalt. So here it's quite different. The capsules will have to be very different. For the case of asphalt, they have to resist very high temperatures. And because you have cars going on the top, you have dynamic loads. So the question is, well, why shouldn't we try it in soils? Because soils are porous. So they have pores, they have holes there. So perhaps we can put these capsules inside of the pores. And then we find a way we have to trigger the release of a cargo, which will then fix the soil. And this is what we are currently working on. So the very first question is, a big advantage of soils is that they are porous. So you can put the capsules inside. But because they are porous, it also means that the capsules can flush away with rain, with water, with infiltration. These are capsules manufactured by us. They are quite large. This is just an example of sand grains, and you have pores there. So obviously these capsules are quite large, but we can make them smaller and fit them inside. So what we did here was try to come up with a way to minimize losing capsules in the soil, simply because the soils are very porous. And this was a study conducted recently, and it makes use of this, well, constriction size distribution. So what this means is that we have to look at the pore sizes in the soil, and we have to match the pore sizes in the soil to the microcapsule size. We have to make sure that the capsules are not too small, because if they are, they will just run away. If they are too large, they will break if you try to squeeze the soil, or you will not be able to infiltrate it. So this study involved conducting washing tests with capsules and soils and proposing a method to deal with this. Okay, so this was then the presentation, and I'm getting to an end. So hopefully, I presume most of you know about soils. I guess the point here is to show that soils are important. They can also be interesting. We know quite a lot, and there is quite a lot right now being done on this, bioengineering. I mentioned the use of vegetation, biocementation. We are moving towards other solutions. Here we are working on this, but there is other people out there, including in Hong Kong, also starting to work on surfaces. I think I cannot see why this shouldn't happen. Of course, there is a long way to go, but why shouldn't we be dealing with or treating soil as a material, and you can heal it, you know, it just heals it by itself. But obviously, before we gather all this knowledge, we still need to, before it comes into application, we'll need to manufacture whatever the, either the capsules or the coatings. we'll have to do field trials, and then we'll have to assess the performance in the fields. So only after this, these technologies will be able to come into practice. And I just wanted to say thank you. So actually, all this work was conducted by former and current PhD students and postdocs, and 4 of them are just here. And they have been very patient with me, and I'm grateful for that. And also, different funding agencies. It first started in the UK, and more recently here in Hong Kong, and obviously University of Hong Kong, because it has allowed me to work on these ideas, and that is always good. So thank you very much.